Hello class, this is my presentation on black holes and dark matter. Firstly, we will go over the history, the mechanics, and the physical principles of black holes in this presentation. So to begin talking about the history of black holes, we will talk about Carl Schwarzschild. In 1915, in December, during the Great War in Europe, he picks up the reports of Albert Einstein and sees the unsolved equations of the general theory of relativity. Schwarzschild then dies due to skin cancer nearly a year later. However, he leaves behind the answers to these unsolved equations. Within these equations, Schwarzschild found he deduced that matter that is compressed so dense, is surrounded by a region of space in which nothing can escape from. This is now called today the event horizon. The radius of the event horizon is coined the Schwarzschild radius due to his discovery. So continuing on, John Wheeler first called a black hole in 1967. He's the person on the bottom left. Before that, physicists would call black holes frozen stars. During this time, most physicists still believed that black holes couldn't actually exist in reality. And then late 1960s, X-ray astronomy was introduced, in which rockets and satellites that can escape Earth's atmosphere are launched, and they block all of Earth's X-rays, so only rays from space can be received. In 1964, one of the brightest X-ray sources in the sky, the constellation Cygnus X1, which is the picture on the top right of what they think it looks like. This was discovered, but its origin was unable to be pinpointed. In 1970, NASA's Uhuru X-ray Explorer satellite was launched and was able to continue narrowing the places these bright X-rays couldn't be coming from. It was discovered that Cygnus X1 was emitting X-rays on a timescale less than 1 second, and something so compact was emitting some of the biggest rays these astronomers had ever seen. Shortly thereafter, within a year, a similar counterpart of Cygnus X1 was found, in which they measured the mass of by using the Doppler effect of the orbiting star's spectrum. By doing this, they found that the constellation that's similar to Cygnus X1 was 15 times the mass of our Sun. So, putting all this together, the speed of the X-ray emissions, the strength of the rays, and the large mass estimate of Cygnus X1 made it a great candidate for the first ever black hole. It is now dubbed a stellar mass black hole by NASA. So, continuing on with the history of black holes, Messier 87, this photo that was taken April 10th, 2019, is the first ever black hole image of a humongous black hole, 6.5 billion times the mass of the Sun. It took 8 telescopes around the globe working as one just to take this photo. These astronomers are not dumb. This photo is extremely hard to take, and we've done it. So we're just entering the field of exploring more about black holes and uncovering more about these anomalies. Yeah. So now we'll be moving on to the mechanics of a black hole. So now we'll be talking about escape velocity. For this example, let's say you are a person who throws up a rock, let's say 5 meters per second. So it's just going to come back down to Earth, right? Let's say you were Superman, right? Big strong man, huge arms, throws the rock up at approximately 11.2 kilometers per second. If it sustained this speed, it would actually not come back down. It will leave Earth's gravity. This number is Earth's escape velocity. But if it sustained the speed, it would not fall back down. It would actually just keep going up into the space. So to expand upon that example I just showed, the escape velocity is dependent on the mass of the planet. So the higher the mass, stronger the gravitational pull, the stronger the higher the escape velocity is going to be to escape that gravitational pull. Um, yeah. So we'll be moving on to the anatomy of a black hole. The accretion disk is basically just a disk of gas and dust around the center of attraction. Actually, due to friction, the gas becomes so hot it starts to emit radiation. And the event horizon is basically the point of no return. Once you go in, there's no going out because, as we just learned about escape velocity, within the horizon, the escape velocity is greater than the speed of light. So nothing will ever go out unless we find something that's somehow quicker than the speed of light. Relativistic jet is just a jet of particles that move close to the speed of light. A singularity is a point in the universe where density of matter and magnetic field are infinite. The center of black holes, for example. Yeah. So now we'll be talking about the creation of black holes. Speed of light is given, and if an object's radius is smaller than its Schwarzschild radius, it's classified as a hole, in which within the event horizon, as we just learned, the escape velocity is greater than the speed of light. Black holes can also be created when dying stars, when the core is crushed by the gravitational force around it, doesn't have the energy to overcome this gravitational force, so it gets compressed and become whole. So, continuing on, the death of a black hole. Black holes emit radiation, Hawking radiation, which is quantum physics. I don't really want to get into that, but black holes emit radiation, so it has to come from somewhere, right? It comes from the mass of the black hole, consequently shrinking the black hole. The rate of radiation emitted from these black holes increases as the mass decreases, and once the mass decreases fully, it presumably just vanishes. So let's say your friend he wants to venture into a black hole, and you're watching from a safe distance. This is a brief summary of what you would see. So as they get closer to the event horizon, they will start to stretch narrower and thinner, and they will start to slow down, but you'll never ever see them past the event horizon. This is because as they get closer to the horizon, at the boundary itself, the escape velocity is equal to the speed of light, so the light will never ever reach you. So it'll just stay there forever. So moving on to white holes and wormholes. White holes are theoretic opposites of black holes. They actually satisfy Einstein's theories of general relativity. It works as a perfectly valid solution. However, it doesn't really mean they exist because white holes are like it's a time reversed version in which they spit out matter. And lastly, wormholes are just connections between white holes and black holes. And since white holes it's next to near impossible they exist, neither do holes. So now we'll be moving on to the physical principles of black holes. To begin the physical principles of a black hole, I'll introduce the Schwarzschild radius, in which the equation to get it is multiplying 2 times the gravitational constant times the mass of the object divided by the speed of light squared. Approximately the sun's radius is around 700,000 kilometers. However, the Schwarzschild radius of the sun is 3 kilometers. So the sun would have to be over 230,000 times smaller to be considered a black hole at the same mass. This should just really show how much of an anomaly these black holes really are, and it's quite fascinating. Moving on, the equation of the event horizon and gravitational attraction from a black hole. Uh, Firstly, the event horizon equation is 2 times the gravitational constant times mass of the black hole, and that gives you the spherical zone of the event horizon, in which you find the point of no return. Next is gravitational attraction, which you get by multiplying the gravitational constant times mass divided by the distance from the center of black hole squared, which is also equal to half the radius of the event horizon divided by this distance from the center of a black hole squared. The value of g at the event horizon is denoted as k, which is half divided by the spherical zone of radius rh, which is also equal to 1 divided by 2 times the gravitational constant and mass of the black hole. We will now be moving on to dark matter, the history and the mechanics of dark matter. So, in 1933, Fritz Zwicky was the first to make observations of modernly called dark matter. He discovered Coma cluster of galaxies, which indicated that there was 500 times more mass in the universe than previously predicted, and this was extra mass that they couldn't see. He called this extra mass they couldn't see Dunkelmaterie, which is German. So, in 1960, she discovered that the outer parts of galaxies don't rotate more than the center, as logic would dictate. So to show this, this is kind of how it would look. It should look how logic would dictate. It's the quickest at the center, and it gradually gets slower and slower, and this is the minimum. But in reality, because of dark matter, it's the max is most likely still in the center, but dark matter continues to push the rest of the galaxy near the same rate as the center. So the dark matter overview, it's next to impossible to detect. We only deduce that it's here due to the gravitational effects it has on the universe. But besides that, based off we can only detect traces maybe based on particle collisions here on Earth and space, if that. It's theorized to exist in the form of an undiscovered elementary particle, such as protons, neutrons, and electrons. Only 5% of the universe is what we can see. 69% approximately is dark energy, and 26% is dark matter. This is something we know next to nothing about, but hopefully, as we continue in our search for knowledge, we finally know what's making up our universe. That's the end of my presentation. Have a good one.